All right, let's talk about a hidden language. It's a secret code that our entire digital world is built on. It's the mathematical key that lets your phone find a song in a crowded room or shrinks a giant image into a tiny file. We're talking about the Fourier transform, and the best way to think about it is like a digital prism for information. I mean, have you ever really stopped to think about how that works? It seriously feels like magic, right? How can your phone listen to this total jumble of sound, people talking, cars honking, and instantly pick out one specific song? Well, the answer isn't magic, it's math. And to get it, you first have to see the world like a computer does. You see, when your phone's microphone picks up a sound, it doesn't hear music or a voice. Nope. It just records a massive, and I mean massive, list of numbers. It's a raw measurement of air pressure changing over and over. And to the computer, this list on its own is completely meaningless. It's just a chaotic stream of data. But here's the thing. The melody, the harmony, the beat, everything that makes that song, it's all buried deep inside that list of numbers. So to find it, we first need to understand this raw, initial view of the signal. This first look is called the time domain, and as you can see, it's basically just a messy-looking waveform. The line goes up and down over time, showing how the signal's strength changes. It tells us that something is happening, but it tells us nothing about what is happening. Honestly, it's like looking at a finished cake but having absolutely no idea what ingredients are inside. So that's the million-dollar question, isn't it? How do we slice open that digital cake to see the recipe? How do we translate this chaotic list of numbers into something that actually makes sense, like musical notes? Well, for that, you need a very special kind of tool. And that tool is the Discrete Fourier Transform, or DFT. Now, I know, it's a complicated name, so just forget it for a moment. The absolute best way to think about the DFT is as a digital prism. It takes a complex, all mixed up signal and perfectly separates it into all of its pure, simple parts. Okay, so here's the formal textbook definition from our source material. But what does that actually mean? It's simple. You know how a glass prism takes a beam of plain white light and reveals that it's actually made of all the colors of the rainbow? The DFT does the exact same thing for a signal. It takes that messy wave and reveals all the individual frequencies hidden inside. It transforms our view from the messy time domain to the beautifully organized frequency domain. And this is what you get. This is what the signal looks like after it passes through our digital prism. Welcome to the frequency domain. See, no more messy wave. Instead, we get this beautiful, clean bar chart. Each bar represents one specific frequency, and its height tells us how loud that frequency is in the original signal. Suddenly, the chaos has structure. We can literally see the notes inside the noise. This is just incredible, but how does it actually work? I mean, how can a mathematical formula listen to a signal and pick out frequencies? Let's take a look at the math behind the magic. Okay, you're gonna love this. The secret sauce inside the DFT is something called the Twiddle Factor. I know, the name sounds a little silly, but it is incredibly powerful. The easiest way to think of a Twiddle Factor is as a perfect mathematical tuning fork. It represents one single pure frequency that the DFT uses to test our signal. This slide breaks down the process beautifully. The DFT basically has a whole collection of these mathematical tuning forks. For every frequency it wants to check, it takes the right tuning fork, let's say for the note A, and it mathematically rings it right next to the input signal. Then it measures the resonance. If the signal contains a lot of the note A, the resonance is really strong. If not, it's weak. It records how strong it was, then moves on to the next tuning fork, building that bar chart one frequency at a time. Now, just being able to see the frequencies is already a superpower. But once a signal is in the frequency domain, we can start to manipulate it in ways that are nearly impossible to do back in the time domain. Our source material points out several of these amazing properties. You've got linearity, time shifting, they're all super useful. But that last one on the list, the time convolution theorem, that one is the true game changer. And this slide right here shows you why it's such a big deal. Now, don't worry about the term convolution. All you need to know is that it's a really complex operation that computers use for things like audio effects or image filters. In the time domain, it's incredibly slow to calculate. But this theorem says that this super complex operation becomes simple multiplication in the frequency domain. It's the ultimate shortcut. It turns a monster calculation into simple arithmetic. But for a very long time, there was one big problem. For all of its power, the DFT had a critical flaw.
For decades, its amazing abilities were locked away because it was just too slow for most real-world applications.
The problem was speed. That direct method of calculating the DFT, testing every single tuning fork for every single piece of data, it takes a huge number of steps. For a signal that's just a few seconds long, the calculations could take a computer minutes, maybe even hours. The tool was powerful, for sure, but way too slow to be practical. And then, the solution arrived, the Fast Fourier Transform, or FFT. Now, this is a really crucial point. The FFT is not a new kind of transform. It is a genius algorithm, a clever recipe for calculating the exact same DFT result, but in a tiny fraction of the time. This table really puts it all into perspective. The direct DFT is the brute force approach. The FFT, on the other hand, is a super clever algorithm that reuses calculations and exploits symmetries in the math. It gets the exact same result, but it gets there exponentially faster. This wasn't just an improvement, it was a flat-out revolution. It was this one algorithmic breakthrough, the FFT, that took the theoretical power of the Fourier transform and finally unleashed it on the entire world. So, the crucial takeaway here is that the FFT made frequency analysis fast enough for computers to perform in real time. It is the hidden engine that powers so much of our modern digital life, from Wi-Fi signals and image compression to, yes, that app on your phone identifying a song. By making the DFT practical, the FFT unlocked all of these fundamental abilities. It gave us the power to see the frequencies inside any signal. It let us surgically remove noise by just turning down its bar on the chart. We can compress files by just tossing out the frequencies we can't see or hear, and of course, we can use that ultimate shortcut of the convolution theorem at lightning speed. The story of the DFT and FFT is just the perfect example of how a beautiful piece of mathematics can completely change the world, but only after a clever algorithm comes along and makes it practical. It really makes you wonder, what other invisible worlds are all around us, just waiting to be decoded by the right mathematical key?